Today you would focus on dot product, and I know you are familiar with dot product, and you happen to know dot product in a certain way. Okay, but we would start by defining dot product of two vectors. So we would start by defining a dot product of two vectors. So this right here is a definition sign. So the dot product is simply magnitude of A and B multiplied together, and then cos of alpha, where if A and B are two vectors, alpha is the angle between the two. Okay. Okay. So a dot product is essentially a mapping from vector space to the space of real numbers. So we take, vector space in this case is R3. So we take two members from the vector space, and the product itself is a scalar. Okay, and it has certain properties. So the first property, which is the so-called commutative rule, okay, which is basically A dot B is B dot A. Now, to prove that, you see B dot A is again magnitude of B times magnitude of A, and then in cos of minus alpha. If the angle between A and B is alpha, then between B and A, it should be minus alpha. But then cos of minus alpha is alpha, which basically is cos alpha, and therefore this is essentially A dot B. Now, then there is a distributive rule for dot product. But before going into that distributive rule, let's focus on the third one, which is a multiplication with the scalar. So if I multiply the dot product this, okay, and that is essentially equal to this dot product, or equal to this dot product right here. Okay. Now, what is the purpose of showing all these proofs is that, yes, I mean, we know these things work with dot product, and since you are familiar with dot product, you know a lot of things can be done. I mean, why not am I writing A dot B as simply summation over I, AI, BI? That's I'm not doing, because we are, as was the plan on the first day, we would forget whatever we have learned, okay, and we would start afresh. So that's what we are doing. And the fact that it has certain properties, the distributive law, or sorry, here there is no distributive law, the associative law over here. Okay, so this is the associative law. This is the commutative law. Okay, so these things work not as separate properties of dot product. They essentially are coming from the very definition of it. Okay, so this single line definition is sufficient for us to give such properties to the dot product. Okay, so that is important to learn. Okay, so then the next thing is the distributive rule. Okay, now this I hope doesn't require a proof, because for each case the expression is going to be this scalar right there, then magnitude of B, magnitude of A, because you see the magnitude of a vector alpha times A is essentially alpha times magnitude of A. Okay, there is no doubt in that. So in each case, it is going to be the same. So no issue in that. And therefore, the associative law works completely fine. Now, what about the distributive law? When we this is a definition of A dot B plus C. Okay, so this basically tells us that this is A dot B plus A dot C. Okay, yes, whenever I say dot product, in your mind probably you are thinking ax bx plus ay by plus az bz, but that very form, okay, is essentially a derivation coming out of this abstract representation. Okay, this doesn't give us much of an information. I mean, it's not very evident from here that it is summation ai bi is the dot product, but you'll see that this essentially progresses into that very representation. Okay. And of course, this is not, all those derivations are not there in your textbook. And but are they important? I think they are important because you are smart people, and you should be knowing that there is no hocus pocus going on here. So A dot B plus A dot C. How is it true? So for that, you need to understand that if I can write this is a unit vector along A, B plus C. Can I write this? That is the question. If I can write this, then writing the above expression would not be difficult, because you see A right here is simply magnitude of A times EA. So a scalar being multiplied to one of the vectors taking part in the dot product. This is the second vector. Okay, so multiplication with scalar works fine. I mean, this associative law works fine. So part of the distributive law is like this associative law. Now, what about the remaining part? Does it work? I mean, does this representation with the unit vector works? First of all, let's see what is taking a dot product with a unit vector really mean. Okay, so this right here is a B vector, and then this is the angle right here. Okay, so EA dot B is, as we can see, is magnitude of EA, which is but unity, then magnitude of B times cos of alpha. Okay, but what is that quantity? If I drop a normal, okay, on the unit vector EA, okay, so essentially okay, I'll not draw the normal like this. Okay, I'll not draw the normal like this. There is a reason for that. I'll explain in a minute. Okay, so just imagine that these two vectors, okay, B vector and EA vector, none of them are lying on the plane of paper. Okay, you are only seeing their projections, and this angle right here, although it doesn't look like a right angle, it actually is. Okay, this right here is a right angle. Okay, because I don't want to do a derivation for planar vectors. Okay, so what does this mean? This since this angle is alpha, this length right here is how much? This length right here is magnitude of B times cos alpha. Okay, so taking a dot product essentially means taking a projection of the vector B on the unit vector EA, okay, or on the direction EA. So taking a dot product with the unit vector essentially means this. Now let us take the second vector, and this is C. Okay, so again, let me extend uh, the unit vector EA, I mean the direction. Okay, so although it might look like C and EA are parallel, they are not. What is basically happening is EA doesn't lie on the plane of B and C. Okay, just to make a general case, EA not necessarily lies on the plane of B and C. So now if I drop a normal from the tip of C, okay, and let's say this is something like the normal. So this length right here, okay, so the two ends of the vector C have been projected on the line EA. So although in this view it is not the true length, but this actually represents C. Sorry, so it is since this quantity is EA dot B, so this quantity right here is EA dot C. Okay, so every time you project the two ends, okay, it's basically going to be that since this one is a unit vector, so this quantity is 1, and then this part is the magnitude of the vector, and times whatever the cosine times the cosine of whatever the angle is. Okay, so that's what the projection is. So this part essentially is EA dot C in the same way. Okay, if okay, so now if I draw the resultant of B and C, and if that is R right here, R therefore is B plus C following the triangle law. So this is the plane of B and C on which R lies. Okay, but imagine just in general, I mean there is no restriction on that A cannot be on the plane of B and C, but in general it need not be on the same plane as B and C. Okay, and still this rule should work, the distributive rule should work. But then if I look at R, this length right here, okay, is essentially R dot EA. Okay. So what we see is EA dot R, which is B plus C, that obeys the distributive law. And since that works, sorry, there's a dot product. And since that works, we can, simply use the associative rule to extend that further to eventually having the distributive law to be proved. Okay. So all coming from this definition itself. Okay. So the distributive law is not some separately imposed condition on the dot product. It's just is the derivation out of it. It's just this graphical representation eventually leads you to this expression. Now, The next part is extremely familiar to you, which is the dot product of the unit vectors. Okay, the Cartesian unit vectors. So I dot I is 1 because uh, the angle between I and I should be 0. So cos, so it is magnitude, of course, because these are unit vectors, the magnitudes are 1. And then if you multiply with cos 0, then eventually you are going to get I dot I equal 1. And same is true for j dot j and k dot k. Okay, so instead of referring to them as I, j, and k, if I refer to them as E1, E2, and E3, then EI dot EJ is actually something called a Kronecker delta. Okay, so what is a Kronecker delta? A Kronecker delta is 1 if I equals j, and equals 0 if I not equals j. Okay, which is obvious since I dot j, I mean this time these are not indices but unit vectors. I dot j is essentially 0 because the angle between the two is 90 degrees and cos 90 would be 0, and so these quantities are zeros. Okay, now I'm not showing j dot I because it's same as I dot j. So what is the significance of Kronecker delta? Kronecker delta is actually the individual terms of an identity matrix. Okay, which means the diagonal terms. So these are the 1, 2, and 3 columns, and these are the 1, 2, and 3 rows. The ij term, the ij term of the identity matrix is Kronecker delta. So the identity matrix is populated by the Kronecker delta. Okay, so little linear algebra right there. Okay, so just you see familiar things, okay, in your other familiar things, which is dot product. So this is how the dot product works with unit vectors. Okay, so we established the three properties of dot product just from the definition, and again from the definition we found out what are the dot products of the Cartesian unit vectors. Okay. Now one more thing. This if I combine the associative rule and the distributive rule, okay. So of course it took us associative rule to prove the distributive rule, but it still is an independent property, and if I combine these two, then I can say A dot alpha times B plus beta times C, that equals alpha times A dot B plus beta times A dot C. And this actually is your complete linear form of the dot product. And this shows that a dot product is completely linear. Okay, it needs to have this scalar multiplication, and then it should have that distributive property. So a dot product is a completely linear operation, and with that and with this, okay, we'll proceed for the most familiar expression of the dot product, okay, which is summation ai bi. So to be there, okay, so if I now take a dot product of A dot B, I need to appreciate that B is essentially summation over BI EI, okay, which basically means BX times I plus, I mean, there are two different notations with of the Cartesian unit vectors. So BY times J and bz times k. So I can use the the linearity of the dot product, and I can say that this is essentially bx times a dot I plus by times a dot j and bz times a dot k. Okay, and then I can use the same linearity of dot product. Okay, and this time I'll be expressing a as uh, summation ai ei, and then be taking dot product with each of the unit vectors. Okay, and be using this linearity of the dot product, which would eventually give me that this is only bx times ax, because all the other terms coming from this dot product is going to be 0. So ay by and az bz. Okay, so that essentially is your summation over I goes from 1 to 3 ai bi. Okay, so is it clear up to this part? Or does this make sense? I mean, you all are familiar with the final set of expressions, but all I'm saying is, looking at this entire thing in a single page, does that make sense?
Yes, yes.
Okay, so now we'll proceed for solving some problems. Okay, so what we have learned about dot product is, one thing is, it is good for giving us the projection of vectors of any vector in a given direction. For example, if I'm given a vector A, and then if I'm given another vector B first, and if I'm asked to find out the projection, okay, of B on A, so what I should be doing is, I'd be taking the unit vector along A and then be taking dot product with B. Okay, that essentially is going to give me the projection of B on A, and vice versa. Okay, you see the projection of B on A and projection of A on B. Okay, would be having similar but slightly different expression. So if I'm taking projection of A on B, that would be A dot B divided by the magnitude of B. And if I'm basically I'm trying to get the unit vector of B. Okay, and if I'm trying to get the projection of B on A, that would be A dot B divided by the magnitude of A. Anyways, since we have already gotten the Cartesian expression of the dot product, okay, that is going to serve us well in the set of problems that we are about to solve. Okay, so look at the first problem, which is figure number 24. Okay, now can you see the figure number 24 quite well? Okay, so your okay, so there is a post right there. Okay, and on that frame, at the tip of it there is a 400 Newton force. Okay. And in the last class we saw how to get the Cartesian component of that force, okay, from the angles that are given. So that will be our first job, and then we have been asked to find out the parallel and perpendicular components of that force in the direction AC. Okay, so how do we do this? So at first, how do we get the Cartesian components of F? So it makes an angle of 45 degree with a plane that is parallel to XY plane. Okay, so and it lies above the xy plane. Okay, which means f sine 45 is going to be the fz component. Okay, now what about the fxy component? That is essentially f cos 45 degree. Now once I have that, that is essentially the projection of f on the plane parallel to xy plane. Now that projection itself makes an angle of 30 degree with a direction parallel to y-axis. Okay, so if y is if cos 45 degree, okay, times cos 30, and if x, okay, is going to be minus if cos 45 degree times sine 30 degree. Why minus? Because the projection lies on the second quadrant of the plane that is parallel to xy plane. So this, that way we would be getting the Cartesian expression of the force. Okay, can you tell me how much is the the force? Don't forget to put the unit in the end. So in I, J, and K, how much is the force?
Sir, negative 100 root 2 I cap.
Okay.
Achha, I will tell it like that. Okay, sir.
Then?
Sir, positive, 1 minute, sir. Positive 244.94 J cap. And positive 200, positive 282.84 K cap.
Okay.
Sorry, 282, sir. Oh, yes.
Yeah, 282.8 is simply the twice of this one, right? Because sine 30 is half. So, so you have the expression for the force. Okay. And now I'm interested in finding out how much of that force is parallel to AC and how much is perpendicular. Okay. So there is a so to get EAC, okay. So at first I need to get R of C with respect to A. And how much is that?
4 J cap plus 3 K cap.
Okay. Okay. So the unit vector?
1 by 5 into the whole thing.
Right? So how much is the parallel part? So that of course is F dot EAC, right? So how much is that value? How much is the dot product?
Sir, 365.659.
Yes, sir. Yes, sir.
365.4?
Sir,
Newton.
0.65 means it would be 7.
Okay, okay. And 6.
65
So,
points? Yes.
okay. So now how do you get the perpendicular part? So basically, this is your post. And pardon my poor drawing. So this is the axis. Okay. And and this right here is AC, and you might want to extend this one. Okay, and this right here, this blue colored line or this green colored line is your force. Okay, and what you are essentially done is took a projection. So this thing is, as we have shown earlier, is equivalent to taking a projection. So this quantity right here is F parallel. Okay, now what is remaining of F is F perpendicular. Okay, so how do we get F perpendicular?
The Pythagoras theorem.
Yes, sir. Sir, it is coming
So-
162.14.
Okay, okay. So 162.1. Okay, so so that again, okay, we didn't discuss, but that is another property of dot product, that if you take dot product of a vector with itself, that actually gives you the magnitude squared. Okay, so square root of F dot F minus F parallel squared, right? Okay, so so this problem was pretty simple, I guess, for most of you. Now, since we are in the topic of dot product, I would like to mention one more thing, and that again is coming from advanced linear algebra. But I believe you being electronic engineers, so I mean. Engineers in electronics, so you would be requiring those, at least some of you who would be pursuing mechatronics or other advanced topics. So so there are so a dot product, as you might be familiar, at times is represented like this. Okay? A dot product. Okay, and it comes from the broader class of product called inner product. Okay, a inner product is okay, is not necessarily defined for vectors. Okay, and I mean the vectors as we know of them, it is inner product is typically a product defined in on a vector space. Okay, where is a map from two elements from vector space to a real number, but the elements of the vector space are need not be the Cartesian vectors as we know of them. Okay, for example, if you have two matrices, okay, let's say let's say U and V are two matrices, okay, of the same size. Okay, so this one is M cross N and this one is also M cross N. Okay, two matrices. So I can define an inner product of UV, which is denoted like, instead of a single dot with multiple dots. Okay, which implies that I'm going from a second order tensor to a scalar. Okay, second order tensor to a zeroth order tensor. Okay, here there is a single dot, which means I'm going from a first order tensor to a scalar, or a zeroth order tensor. So this time I'm going from a second order tensor to a scalar, and that basically is defined something like this: summation over I, summation over j. I goes from 1 to n, 1 to m, and j goes from 1 to n, uij, vij. Okay, so instead of just doing the summation of the product on a single row, you are actually doing that over all the rows and all the columns, because this time you also have different columns. Okay, or if earlier you only had columns, this time you also have rows. Okay, so this comes from a broader class of you see product called an inner product. Okay, the dot product is simply the inner product for the 3D vectors as we know of them. Okay, think about functions and function space. Okay, so function space is you see is the space of all possible functions, and that somehow qualifies, very surprisingly, that also qualifies for a vector space. Okay, it's pretty advanced linear algebra, but mm, uh, you see, so even in that function space you can define an inner product. Okay, I just wanted to show the the generality of inner product. So in that case, the inner product can be, for example, something like this: 0 to twice pi. Let's say one function is sine of x, the other function is sine of 2x. Okay, and if you had already had a course on Fourier series, then you know this integration leads to 0, whereas also this integration leads to 0, and this integration is non-zero. Okay, uh, so you can think of all of these functions, sine of x, sine of 2x, cos of x, as basis functions, just like you had basis vectors with Cartesian vector space. Similarly, you can think of these as orthogonal basis functions. So whenever you do an inner product of two mutually orthogonal functions, basis functions, they eventually lead to 0. Whereas if you take the same function, then the dot product is non-zero, unless of course the function that you are taking is trivially 0. Okay, so that also applies to the dot product that we are talking about, which is one of the inner products. So u dot u, okay, is always greater than equal to 0, and equality only holds when u is trivially 0. Okay, same thing applies here. If it is sine of x, which is not 0 everywhere, between 0 to twice pi, this integration is always greater than 0. Okay, it's not even equal to 0 or less than 0, it is greater than 0 always. Okay, so my point is that the dot product that we are talking about comes from a broader class of products called the inner products. Okay, and let's move on to our next problem. Okay, so figure number 25. It's a pretty difficult image, but I hope you can figure out, or maybe. Okay, so the problem statement here is to determine the angle between the two cables. And the second statement is, what is the sum of the projections of the two forces along the axis of the tower? Okay, so basically there is a tower, and it is being supported by 3 cables, of which in 2 of them we know the value of the forces. Okay, but we are interested in finding out how much would be the angle between the 2 cables. Okay, and for that we do not need the forces. Simply having the the position vectors is good enough. So how do we get the angle? Okay, so for example, this is the cable 1, and
Sir,
yes.
sir, the figure is not visible. Can you please? Yes, sir. Yes, sir. Yes, sir.
Okay, so this is the cable 1. Okay, and if I find out the position vector of B with respect to A, Okay, and again, don't just try to do that directly, because in your mind automatically you would be subtracting RA from RB. So why not write it down on your page? So first get the position vector of B with respect to O, position vector of A with respect to O, and then do the subtraction. And once you have the position vector of B with respect to A, find out the unit vector along AB. Same thing for AC. Then the angle BAC, okay, is the arc cosine of the dot product, right? Because the dot product is, since the magnitude of the unit vectors is going to be unity, so unit vector along AB dot unit vector along AC is essentially 1 times 1 times cos of this angle. Let's call this angle as alpha between A and between AB and AC. So the cos of that angle is essentially the dot product. So from that you can figure out uh, the angle between the two cables. And number two is you are being asked to find out what is the projection of the two forces, okay, uh, along the axis of the tower. Okay, now now the second part can be done in two ways. Okay, you can either be taking individual forces, okay, then be taking the dot product and adding them up. Otherwise you can find out the resultant of the two forces. Okay, and once you have the resultant, then you can take the dot product of the resultant with the axis. And as we have shown earlier, both the methods are supposed to give you the identical result. Okay, so for the second part I need you to check that the proof of distributive rule works, which means take the dot product of FAB with the uh, the axis of the tower, and same thing for FAC. Okay, and add them up, and then compare that value with the resultant of FAB and FAC, uh, taken dot product with the axis. Okay, just check the distributive rule works for uh, you know this case.
Sir, in this one, between which two cables do we have to find the angle?
Sorry.
In this question, in which between which two cables do we have to find the angle?
Okay, AB and AC.
Okay.
Sir,
Yes.
Our angle is coming
angle is
about
90.
38. 38 as
No, 34 sir angle is
Okay. Okay.
44.11.
44. So different values are coming. Okay. So let's try this. Okay. So so let's try it from the beginning. So what is the position vector of B?
44 is correct. 44.11.
44.11. Okay. Anyways, what is the position vector of B? So it is
Sir, 12 by j cap minus 18 j cap.
18I,
Mm.
18I, right? And
18 I cap minus 12 J cap.
minus 12J. Okay. And RA is simply 36K feet, right?
36K cap.
Okay. And RC is
12J cap plus 30 I cap.
no, it's not 12J cap. You see, what it means is that the distance from the origin is 12 feet. Okay. So RC is in X direction. It is sine 30 is half, so it is 6 I, and then it's in the first quadrant, so both are going to be positive. Plus then 6 times root 3, which is 10.4 approximately J cap feet, right? So this, how many of you have got this value? You see, it is clearly showing this, small arc line showing that this distance from the origin is 12 feet. Okay. So be careful with the representation. It's not 12 feet right there. Okay. So from that you can figure out the position vector of B with respect to A. So simply it is 18I minus 12J minus 36K feet. So the unit vector AB, and again here what that square of 7 has been used. So 6 squared plus 2 squared plus 3 squared is square of 7. So it is essentially 3 by 7, which is 0.428 I, 2 by 7, that is 0.286 J, and then 6 by 7, which is 0.857 K cap. Okay. And then position vector of C with respect to A, there you have 6 plus 10.4 minus 36 K feet. So 3 plus 1 plus 3 plus 1. Okay. So this is going to be different. So how much is this one?
Is 0.158 I cap.
Okay.
Uh, 0.274 J cap.
Okay.
It is 0.948 J cap.
No, if the first one is 0.185, the last one cannot be 6 times 0.185 is something else, right?
Mine is coming
It is
0.17.
0.158, not
158. The first one is 158.
yes, sir.
Okay. Okay.
So mine is coming 0.17.
The first one.
Yes, sir.
Okay. So is the magnitude 6 root 40, which is basically 12 root 10. Which is
Yes,
approximately
it is 12 to
38, approximately
37 point.
37 point something, right?
Yes.
So you're dividing everything with 38. So, okay. So just check that is the correct one. So what is the third component, Z component?
0.948.
948. Okay. Okay. So 6 by 38 is going to be something like this, not 0.174 or something. So this is the value that you have. Okay. Now try to get alpha, which is cos inverse dot product of this two unit vectors. And how much is the angle then?
44.11.
Okay.
The projections are coming 600 Newton and 660.20.
Okay. Okay. And if you, okay. So basically you are comparing the K components, right?
Yes, sir.
So this one you are multiplying with 700 EAB. So you are going to get 600, right? With AB
Yes,
it is
sir.
going to be 600. And on this one you are multiplying with okay, 600. So around 570 or something, right?
Mine is 660.20.
No, it is 600 LB. So the K, the Z
Sorry, I
component.
have taken 700.
Sorry.
I had taken the force along AC 700. That is why.
No, the force along AC is 600, right?
Yes, sir. I made a mistake.
Okay. So it is going to be somewhere close to 570, actually smaller than 570. Okay. So just check how much.
568.8.
Okay. Okay. So you basically need to add them up. That would be, the complement along the
1168.8.
axis. Okay. Actually, if it is, the component along the axis, then you can directly take the Z component. But instead, if I had asked you to give me the component along AD, okay, there you probably have to, you could probably, verify your distributive law. Anyways, so let's move on to the next problem. Which is figure number 26. So you see that 300 Newton force F there. Okay. Now please understand where it is lying. Okay. So the structure that you see there, the whatever you want to call it, clamp or a frame. So starting from the origin, it is initially along y-axis. Then it takes a turn parallel to negative x-axis, and then it makes an angle of 30 degree with the vertical vertical axis. Okay, so on that plane F lies. On that plane F lies and makes an angle of 30° with a direction which is parallel to y-axis. So that means the y component of F can be readily obtained, which is F cos 30°, or F times root 3 by 2. But then the sine component is not along either z or x. It is along a line which is making an angle of 30° with z-axis. So if sine 30, okay, is the the component parallel to that plane. I mean, of course, the cos 30 is also parallel to the plane, but all I'm saying is it is parallel to the line that is making an angle of 30°. Okay, so then that f sine 30° needs to be multiplied with cos 30° to get the z component, and if sine 30° then multiplies to sine 30 to give you the component in negative x. Okay, so try to get the at first get the the Cartesian representation of f.
Excuse me, sir.
Yes.
Yes, sir. If is coming minus 225 I cap
Okay.
plus 150 J cap and 129 K cap.
Minus 220
225.
minus 225 I cap.
Yes,
I'm not
sir.
convinced.
Okay, sir.
It's minus 75 I cap. Just check.
Sir, F is coming minus 75 I cap plus 75 root 3 K cap plus 150 J cap.
Okay. 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 Acha. And what about the position vector of A?
So that's minus 450 I cap plus 300 J cap plus 150 root 3 K cap.
450 I cap is fine.
300 J cap
300 J cap is also fine. And
plus
then
150 root 3 K cap.
150 root 3 K cap. Okay.
It is
Mhm.
3.
Okay. So now you can get the unit vector along OA
Yes, sir.
and then get the
The projection is coming around 242.4.
okay. I don't have the answer, but as long as you are doing the correct steps, you are going to get correct result. Okay. So the F seems right, and also the position vector seems right. So I guess the answer is also correct. Acha, now I just want to give you one more example on getting
Sir.
projections. Yes.
Sir, what was the expected value? What did he say?
Sorry. What
Sir, what
value?
was the answer?
I don't know. I don't have the answer. I mean, I don't
Minus
even.
coming 240.
Excuse me, sir.
I'm getting 242.4 Newton.
Yes, sir. That's the one I was.
Okay, maybe. Okay. Okay. So one more example I would like to give you. Okay. So can you think of getting a projection of F along AB, or whatever would that mean? So basically, it's all in a box of sides A, B, and C, and can you find out? I mean, of course, you can find out the Cartesian components and all, but you see, because in all the other examples, the line along which are you supposed to take the component, the component, parallel component, is actually actually coincidental with the force, okay, or concurrent with the force. Okay, they are at the same point, intersecting, but this time it's not. Okay, so in this case, what do you make of when I ask you about the parallel component. What is meant by that?
So these are skew symmetric lines. Dot product is not possible.
Dot product is not possible? Who is stopping you from doing the dot product? I mean, can you not get the unit vector alone? Can I not get the the Cartesian representation of F? Can I not get the Cartesian representation of AB?
Yes,
And
sir,
what is
but they have to be coincident, na? They have to be
Why?
at least on a plane. They should make a plane,
Why should they make a plane?
or else, sir,
Sir, can
how
you
can we
repeat the
find the
question?
angle between those two?
To have the angle between these two, you see, the idea is that
So we can consider it as a free vector and
yes. So the idea is that let's say this line right here. Okay. So if I so when I took for this force F right here. Okay. So in the the figure that is there. Okay. When you determined the x component of it. Okay. Did you actually get the angle with the x-axis? No, right? You just took or let's say when you got the y component of it. Okay, when you got the y component of F. Okay, so you are actually using it. Did you actually measure the angle of F with y-axis? No, right? What you simply did was took another line which is parallel to y-axis, and then you took a projection on that line. So by your logic, I shouldn't be able to get the y component of this force, and the y component of this force doesn't exist because you cannot do dot product of F with J. The thing is, I can always draw a line parallel to AB, intersecting with F, and the angle that we are talking about is not between the exact two vectors. Okay, one of the vectors can be moved parallelly to intersect with the other. Okay, number one, and number two is the very essence that the dot product with the unit vector is essentially a projection. That also is not restricted because I can always drop perpendiculars from any point to the straight line. Okay, and since I can get a projection, okay, so the dot product is also defined. Okay, so when I do not have the exact line, I'll take a parallel line, and I can take the dot product there. Okay, so yeah, so with that much, more or less, I think we have covered some examples with dot product, but of course you'd be needing more practice, and you'd realize as the days goes on that problems are becoming slightly difficult than the previous class, and you should be at this point, your job is to be patient because I'm still covering pretty basic stuff, and you might think it's all very obvious, but still you should be practicing more and more problems from whichever textbook you want. So as long as you don't have the confidence that you can solve any problem on your own, so just go through the exercise of the book. Okay, so with that we can proceed next for defining moments. Okay, and this is how the textbook defines a moment. Moment is a tendency of rotation, and what it basically means is, so when you apply a force to an object which has finite dimension, the effects, if it is a particle, as we know, that the particle could either be in equilibrium, or it could be an acceleration, but a linear acceleration. But when an object is you know has finite dimension, on application of a force, there can be effects more than simply having an acceleration. Okay, it could also rotate or tend to rotate. Okay, or it could develop a tendency of rotation. That means if it is not supported by some means, okay, some support rather, so it would start rotating, okay, or start developing an angular acceleration, so to say. So this tendency of rotation, as it turns out, is dependent on two quantities, okay, and two quantities, and actually turns out to be proportional to both the quantities. Okay, the one quantity is obviously the amount of force that you are applying, and the other quantity is actually the distance from the potential center of rotation. Okay, every time all I'm doing is saying a potential center of rotation, a tendency of rotation. It's because the actual rotation may not happen and the moment can still be there. Okay, so a moment, okay, is defined about a given point. Okay, that given point is essentially what we are considering a potential center of rotation. So moment about that point is dependent on two quantities: the magnitude of the force and if you drop a normal on the force from that point, so that normal distance. Okay, and the tendency of rotation. Okay. Tendency of rotation kind of follows the right hand rule. What is basically meant is that if you look at it from the top, okay, okay, how do I explain this? Okay. Okay. So two things. One is that the tendency of rotation, or the moment, the value of the moment, is proportional to two quantities that we just mentioned. The other thing being that the rotation tends to take place. The rotation tends to take place on a plane containing that normal distance and the force that we are talking about. Essentially, the potential center of rotation and the force itself. Okay, so it contains that plane. Now, every time we have a plane, we can think of a normal to that plane. And what we instead, since we and we can think of that normal being the representative direction of the plane, and therefore we can think of a moment being a vector. Okay, and moment being a vector whose magnitude again is proportional to the magnitude of the applied force and the normal distance, and the direction is normal to the plane containing that potential center of rotation, or the point about which am I getting the moment, and the force. Okay, whatever the plane is, whatever plane contains those two, it is normal to that. Okay, and with we use right hand rule, okay, to put a sense to the moment, whether a moment is positive or negative. There is a sense. To put a sense to the moment, we use the right hand rule. If the moment is going to be counterclockwise, if the tendency of rotation is going to be counterclockwise, if we look at that plane from the top. Now, what do I mean by top? That means if I consider the normal is upwards. Okay. Now, of course, in the figure that is shown, it's kind of the ground, which is the plane of the moment, and of course the normal is the vertical line going upwards. So it is literally the upward direction. But here I'm not talking about this special scenario. I'm talking about every situation when there is a force trying to cause a moment. Okay. So look at the if you're the direction of the moment is the one. Okay. If you were to sit at the arrowhead of the moment and look at the plane, okay, the moment would appear counterclockwise. Okay. So that would be the direction of the moment. Okay. But if you are sitting at the top of the arrowhead, okay, representing the normal to the plane, and the moment appears to be clockwise, then the moment is actually in the direction opposite to the normal. Okay. So so is this part clear?
Sir, what is the difference between moment and torque?
Absolutely no difference. So
Sir, then আলাদা করে মানে বলে কেন এরকম ভাবে?
I'm not quite familiar with the terminology. I mean, they are the same, right? Unless, of course, you're talking about a couple moment, that's a different situation. But when it's a couple moment, you literally mention that it's a couple moment. Okay. But otherwise, in either case, the moment or torque both are formed by applying an external force, and both treated as vectors. So I don't see why there should be any difference. Okay. Okay. So and let's say if I have more than one force on a given plane, then actually I can simply add the moments formed by them. Okay. If all the moments are forming on the same plane, that means all of them have the same normal. So all I'm doing is stating the obvious, that in that case, simply the algebraic sum of the moments would give me the resultant moment. If that is not the case, then I should be doing a vector sum. Okay. And that vector sum would give me the resultant tendency of rotation. Okay. So later on, you'd see again one more obvious thing, that the cross product is the most efficient way of representing a moment. But before going into that, let us introduce ourselves to cross product. Okay. I believe there are two more problems. Okay. Without using the cross product. So problem number 30 and problem number 31. We will do them today, and in the next class we will proceed with cross product. Okay. So for problem number 30, the job is to find out a net moment about point A. Okay. And here also we don't have to do the vector sum. Okay. It's because the plane of F and A is the same plane as P and A. So both the moments are lying on the same plane. One may be positive, the other one may be negative. Okay. Now, if you consider the plane of the screen to be xy plane, and if you are sitting at the tip of the z axis, okay, then whichever moment is counterclockwise, you'd treat it to be positive, and whichever moment is clockwise, you treat it to be negative z. Okay, so from this point onwards, I need you to treat moments as vectors, and which means that the moments are simply not values like a scalar. Okay, although you are only familiar with, mostly you are familiar with, 2D moments, which are basically about moments about z axis, and therefore can be treated as a scalar, and just has positive and negative sign depending on the clockwise and anti-clockwise sense. But this point onwards, I need you to treat moments as vectors, and every time you write a moment, even on a xy plane, you simply put k hat next to it. Of course, the moment has its own set of units. For example, in figure number 30, the unit should be pound foot. Okay, so you can take F to be 200 pound and P to be 150 pound. So F is 200 pound and P is 150 pound. And now try to get the moment due to two forces about point A.
So can you please repeat the forces again?
Yes. So F is 200 pound and P is 150 lb.
Okay, sir.
You cannot use cross product, by the way. So here it is still dependent on having the normal distance. By the way, we just said that if you have coplanar forces, okay, then you could be taking, if there are coplanar forces, so you could be taking individual forces, okay, and taking the moment of them about a given point and sum them up. The algebraic sum of it, okay, should give you the moment about all the forces about point A, which means I can also resolve F into its x and y components, okay, and then be taking moment about point A, right? Okay, there's the same method that we were using to sum the moments due to F and P. I could be using that to sum the moment of Fx and Fy. Same thing applies to P.
Sir, what was the value of P?
150 lb.
The torque of P is coming 1909.18 kg.
Sorry.
Torque of P is oh sorry. I made a mistake.
It would be somewhere around 190. What should be the unit of moment? It is pound foot. Okay. Where is the other unit? Both have the same dimension, by the way. What is the second unit for foot pound?
Work.
Work or energy. Okay. So please remember, it is pound foot, the moment.
The torque of P is coming 1909.18 kg.
Maybe.
Yes, sir.
And
Yes,
The
sir.
other one is minus
Minus
190 kg.
Sir, the net moment is coming 10.5 in a clockwise direction.
okay, I don't have the answer, but
Into the plane, yes.
okay. Okay. So then we can move for the next problem, and in the next class we'll be starting with the cross product. Okay, so here in problem number 31, you are being asked to find out the angle theta such that the moment of this force about A is going to be 10 kilonewton. I have written the unit wrong. It is 10 kilonewton meter. Okay, the moment is supposed to be 10 kilonewton meter. Okay, so what angle should give us a normal distance of 2.5 meters? You see, the force is 4 kilonewton. The moment is supposed to be 10 kilonewton meter. So the normal distance on the line of action of the force from A. So basically,
Sir, do we have to like use the Pythagoras theorem to is
you can use that.
we
Absolutely
have to
fine.
use that?
Sir, is it 98.53 degrees?
I don't have the answer. Just check on your own.
Sir, it is 90 plus tan inverse of 0.45 by 3.
Achha, did you consider this 0.45 meter of distance?
Yes, sir.
Okay. Okay, so what you do next is, okay, you simply introduce cross product. Okay, now a cross product is a map from V cross V to V, which basically means you take two elements from vector space, take a product, and the product itself is a vector. Okay, so so that's what we have here. Okay, C equals A cross B, and and what is this? This basically, this statement right there is actually the definition. Okay, this is how you define in cross product. Every other property of cross product would simply come from this. Okay, just like we did in the dot product. So magnitude of C is A B sine theta, magnitude of A, magnitude of B times sine theta, and the direction is obtained by right hand rule. So basically C is supposed to be normal to, much like the moment, direction of moment. C is like perpendicular to the plane containing the two vectors A and B. Okay, and this is how the direction should be. It follows the right hand rule. So so if you move counterclockwise from A to B while going from A to B, okay, then then the direction is in the positive side of the normal, or otherwise it is in the negative side. Okay, so if your fingers curve into the direction of going from A to B, your thumb points towards the direction of the vector. Okay, and the commutative law is is pretty obvious, because sine of minus theta is minus sine theta. Therefore, B cross A is definitely minus A cross B, and the associative law is also very evident. So the commutative law doesn't hold, but that not holding thing is pretty obvious because of sine theta. The associative law is also pretty obvious because it's simply a multiplication with scalar, and that you can club with any of the vectors. Okay, so the product vector or vector A or vector B, whatever. So that works. Okay, and the next thing is the distributive law. Now, distributive law is valid, much like dot product, but again, that also comes from the very definition of cross product. Okay, so so that I leave you to prove. Okay, so apart from practicing, at least 5 problems from each topic that we discussed today, which is basically the utilities of dot product and how you define moments for planar vectors or planar forces. Okay, so do at least 5 plus 5, 10 problems on these 2 topics. Okay, separate from these ones, the ones that you have solved in the class. I am giving you this additional assignment to, you can also search in the internet for the proof. How to prove the distributive law, okay, the validity of distributive law in cross product. Okay, are you already familiar with the derivation? Anyways, you are free to look in the internet for the derivation, and it's important for us to realize that actually the distributive law is also coming from the very definition of the cross product. So we'll proceed with that. So in the next class, we'll start from there. Okay, so you see how the cross product would efficiently represent the moment, and later on we would simply be using cross product to represent moments. Okay, so that's that we'll be doing from Wednesday. Okay, so we'll meet on Wednesday, right?